Hello everyone. Today we will discuss about direct and bending stresses under the subject of theory of structure part 1, presented by myself Professor Khamkar UB, working as a lecturer in Department of Civil Engineering, Vishweshwaraya Abhiyantriki Padvika Mahavidyalaya, ALMALA, Latur. Now see what are the contents in this chapter. First, concept of axial load and direct stress. Second, concept of eccentric load and bending stress. Limit of eccentricity, stress distribution at base. Middle third rule and core of section. And procedure for determination of stress in various compression members. So let's move. First, what is axial load? When a load whose line of action coincide with the axis of member, then it is called as axial load or direct load. Direct stress. The stresses produced due to the axial load is called as direct stress. It is denoted by sigma 0 and its unit is Newton per mm square. The direct stress is calculated by formula sigma 0 is equal to P by A. Next term is eccentric load. When a load whose line of action does not coincide with the axis of member, then it is called eccentric load. And due to this eccentric load, the bending stresses are developed. Bending stress. The stresses produced due to eccentric load is called as bending stress. The bending stress is denoted by sigma b and its unit is Newton per mm square. The bending stress in the compression member is calculated by formula sigma b is equal to m by z, where m is bending moment and z is section of modulus of that particular section. Now, what is the difference between axial load and eccentric load? We will find by figure. The figure shows the example of axial load and eccentric load. First, the example of axial load. This is one compression member, this is a elevation, and this is a plan or cross section of that compression member. These are the axes of that member. The load P is acting on the axis of member, therefore it is exactly at the CG of that member. This is load P which is acting on CG of that member. So by this, in figure, a column is subjected to axial load P, hence there is only direct stresses are generated, and these direct stresses are calculated by sigma 0 is equal to P by A. Now see the next example of eccentric load. Consider another compression member, elevation and cross section. This is the axis of member. The load P is acting at a distance of E, which is called as eccentricity, which is shown in this point. The axis or CG of that member is at this point and load is acting at this point. The distance between CG and load axis of load is called as eccentricity. Due to this load, in figure, column is subjected to eccentric load P at a distance of E from axis of member, hence there is direct as well as bending stress are developed. Now what is eccentricity? It is a distance between the axis of member and the point of loading or axis of loading is known as eccentricity. It is denoted by small e. Limit of eccentricity: the maximum distance of the load from the center of the column such that if load acts within this distance there is no tension in the column. The distance is said to be limit of eccentricity. Maximum and minimum stresses at the base of column or compression member. When a column is subjected to eccentric load, the edge of column towards the eccentricity will be subjected to maximum stress, that is sigma max, and the opposite edge subjected to minimum stress, sigma minimum. How calculate the sigma max? The simple formula is sigma max is equal to sigma 0 plus sigma b. Here sigma 0 is direct stress and sigma b is bending stress. Sigma 0 is calculated by P by A and sigma b is calculated by M by Z. Therefore sigma max is equal to P by A plus M by Z. Sigma minimum is equal to sigma 0 minus sigma b. That means direct stress minus bending stress. Therefore P by A minus M by Z, where M is calculated by using force into eccentricity, that is moment is equal to force into eccentricity, and Z, which is depends on moment of inertia, that is Z is equal to I by Y. Now see the different examples of maximum and minimum stresses. Consider this is a one section having B and D. This is a axis of member and load P is acting on right side of the axis of YY at an eccentricity of E. Now see the position of maximum bending stress and minimum bending stress. The load is acting right side of the y-axis, therefore maximum stress is on the right side and minimum stress is on the left side. Now move for the next example. In this example the load P is acting on x-axis but left to the y-axis, therefore the maximum stress is developed in left side and the minimum stress is developed in right side. If the load is acting on y-axis and above the x-axis, then the maximum and minimum stresses are as shown in figure. And if load is acting on y-axis but below the x-axis, then the maximum and minimum stresses are as shown in figure, vice versa. Stress distribution at the base. Case 1. If direct stress is greater than bending stress, that means sigma 0 is greater than sigma b, then the diagram of stress distribution at base is totally compressive in nature. That means sigma max and sigma minimum, both values are in positive, that is in compression. Therefore the whole diagram is below the line. Hence it is called as compressive nature diagram. Case 2. If direct stress is equal to bending stress, that is sigma 0 is equal to sigma b, the case is also called as no tension condition. Hence in figure the sigma max is totally compression in nature but sigma minimum value is 0. Hence it is called as no tension condition. In no tension condition, sigma minimum is always equal to 0. In both cases the nature of stress distribution diagram is totally compressive. Case number 3. If direct stress is less than bending stress, that means sigma 0 is less than sigma b, then The stress distribution diagram is partially compressive in nature and partially tensile in nature. The sigma max is below the line and sigma minimum is above the line. The nature of sigma max is compressive and the nature of sigma minimum is tensile. What is middle third rule or core of section? It is the centrally located portion of a section around the center within which the line of action of load must act so as to produce only compressive stress is called as core of section or middle third rule. First, what is middle third section of rectangular column or rectangular section? Consider this is a rectangular section of width B and depth D. In this is the middle third rule or core of section. It is also known as kernel of section. The dimension of kernel of section is B by 3 and D by 3. The total width of this section is B by 3 and total height of this section is D by 3. Within this section, if load is acting, then it will produce only compressive stresses. Now, what is core of section for circular section? This is the example of circular section in which the diameter of section is small d. Therefore, the core of section dimension or diameter is d by 4. Within this d by 4 distance or diameter, if load is acted, then it will produce only compressive stresses. In this case, the load is acting on y-axis. Therefore, to calculate section of modulus, we take the axis xx. Therefore, zxx is equal to ixx divided by y, bd cube by 12 divided by d by 2. Therefore, zxx is equal to bd square by 6. Now, step by step procedure for determination of sigma max and sigma minimum for wall subjected to lateral wind pressure. The same procedure is followed as previously. Now, how to calculate section of modulus for wall on which lateral pressure is exerted? Case 1. If pressure is acting on smaller side, that is on D or thickness of section. This is a one wall in which this is the height of wall and the dimension of wall is B and D as shown in figure. This is the axis of members and the height of wall is H. Let consider the lateral wind pressure is acting on the smaller edge, that is on D. This is the wind pressure intensity which is denoted by small p. Then how to calculate section of modulus? In given case pressure is acting on D, then take a cube of opposite side, that is B, acting and the pressure is acting on Y. Let's see. The pressure is acting on D or this face. Therefore, we take the cube of this distance, that is B. Therefore, ZYY is equal to dB square by 6. By solving all this calculation, we get the value of ZYY dB square by 6. Now, case 2. In case 2, if pressure is acting on bigger side or that is on B, this is the example of wall. In this, the pressure is acting on width. Therefore, we put the width in vertical direction and the depth is in horizontal direction. This is the dimensions of wall. The pressure is acting on B. Therefore, we put the width in vertical direction and depth in horizontal direction. This is the pressure which is acting on the width of wall. Therefore, ZYY is equal to BD square by 6. In first case, we square or cube the width of the wall. In this case, we square or cube is depth of the wall. Example to calculate section of modulus. Let's see how in example we calculate the section of modulus. Consider this is a wall having dimensions 1.5 meter by 4 meter and height h, and the pressure is acting on 1.5 meter side. The side on which pressure is acting is 1.5 meter. Therefore, we will take the cube or square of 4 meter side. Therefore, the section of modulus in this pressure is acted on 1.5 meter side. Therefore, Z is equal to 1.5 into 4 square divided by 6, that is Z is equal to 4. In this we will take the square or cube of the opposite side on which the pressure is acting. Now see how Z is calculated if the pressure is acting on 4 meter side. This is a wall having dimension same 1.5 meter by 4 meter and height h. If the pressure is acting on this 4 meter side, in this way the pressure is acting on this 4 meter side, then we take the square or cube of opposite dimension, that is 1.5 meter. Therefore, Z is equal to 4 into 1.5 square divided by 6, that is Z is equal to 1.5. Simply, how we remember these terms? When a load is acting on axis, take a moment of inertia of opposite axis on which load acts. That means if load is on x-axis, take moment of inertia of y-axis, and vice versa. That means if load is acting on x-axis, then we will take moment of inertia about y-axis, and if load is on y-axis, we will take moment of inertia about x-axis. This is for the column load acting on column or eccentric load acting on column. When a wall is subjected to wind pressure, take cube or square of opposite side on which pressure is acting, which is previously seen in the example. Thank you. In part 2, we will discuss or we will solve some numerical based on this theory. Thank you.